Hello, my name is Frits de Mul and this is a presentation about light scattering by particles, theoretical aspects. The contents of the talk are: in movie part 1, an overview of scattering functions, plots of various examples, and in movie part 2, appendices, derivation of the dipole radiation formula and derivation of the general scattering equation. Literature can be found in the book of Van der Hulst, Light Scattering by Small Particles. It's a rather old book, but it is very appropriate for this subject. Contents of movie part 1. First, an overview of the scattering functions, Huygens, the general expression, dipole scattering, Rayleigh-Gans, me and various other expressions, and plots of various examples. We start with some definitions. First, the incident intensity. The scattered intensity, I of omega, in which omega is the solid scattering angle. And we define the scattering cross-section sigma per particle in square meters or microns. That is the apparent effective shadow area for scattering. And that sigma may be dependent on the angle of scattering. It is expressed in d sigma d omega, the differential scattering cross-section. And now we can write that the I of omega, when we have one scatterer, is d sigma d omega times I naught, expressed in watt per steradian, square meters per steradian, and watt per square meters respectively. We can define a total scattering cross-section by integration over the solid angle. Further definitions. Suppose the incident beam is parallel to the z-axis. We have written I of omega expression, and now we define scattering angles. The polar scattering angle measured from the z-axis, theta, and the azimuthal angle measured in the xy plane, that's phi. Now we can define a scattering function, p of theta and phi, and we can write I of omega is the scattering function times the incident intensity, and that scattering function is normalized over space to 1. Further definitions. Here is the situation with theta and omega. The wave factors, k0 and ks, also denoted by k without the s. K is 2 pi over lambda, the wavelength, and we can define scattering and absorption coefficients, mu, expressed in 1 per meter, and connected with the scattering cross-section by this relation in which n is the number of particles per cubic meter. The Lambert-Beer law holds for absorption, and that is an exponential with the mu in the exponent. We can define attenuation coefficients. For scattering, mu of sigma, absorption, mu of A, and total. And the mean free path is defined as 1 over mu total. The albedo is defined as the relative contribution of the scattering to the total attenuation. Scattering in tissue is predominantly forward, and that can be seen in calculating the average cosine of the polar scattering angle, and that's called G factor, and for tissue that's almost always larger than 0.9, and that is seen in this figure here, in which the scattering is sketched. This means that the scattering function P is sharply peaked at a value 1 for theta is small. And please note, this is a logarithmic scale. We can define a reduced scattering coefficient is 1 minus g times mu s, and that's much smaller than mu s itself because g is close to 1. We can define a transport mean free path that is denoted with L of t, is 1 over mu f prime plus mu a, and that is much larger than the mu fp, as is seen here. Mu fp is connected to one scattering event, and LT is connected to the distance, where can be supposed that the photon loses its initial direction. This is an overview of the theories. Electromagnetic, dipolar, Rayleigh-Gans and me. We have other scattering functions, mostly empirical, some advanced models, but there are a lot more models than that, and fundamental transport equation and diffusion approximation, but we will not deal with this in this presentation. First, the principle of Huygens. Huygens' principle deals with the field propagation by spherical waves emitted by all points of the wavefront. Here is that wavefront 1, and that emits to wavefront 2. And Fresnel derived a long time ago that the disturbance from any point of plane 1 to any point of plane 2 at the mutual distance r is given by a spherical wave, and the spherical wave has a phase factor minus ikr in the exponent divided by the distance r. Fresnel called it disturbance because at that time the notion of an electric field was not known yet. Let's integrate over plane 2, and then the disturbance caused by disturbance E0 present at the wavefront area element here in ds. In a point at the distance r from ds is given by this expression, is I over r lambda times the phase factor times ds times E0. And please note that factor I can be written as the exponent of ip over 2, and that means that it causes a phase shift of ½ pi in the scattered wave, and that means that cosine and sine interchange. And this is the basic formula for all light scattering theories. We start with electromagnetic theory from Maxwell's equations. Here are those equations. The two divergences are 0 because we do not have a charge, and the rotation of the electric field is minus dB dt, magnetic induction, that is Faraday's law of induction, and here we have Maxwell's fix with the d dt, and d is the electric displacement, and there is no current, and therefore this equation holds. We can derive by taking this expression nabla times b and this expression together. We can write that the rotation of E is minus mu naught times the time derivative of d, and this is called rotation. It's also called curl. Now we insert material properties, and those material properties are that d is as a function of r and t is epsilon times E, and epsilon is given by epsilon naught times E plus epsilon 1 plus epsilon 2, etc., but we will skip those higher terms. The fields are given by E0 incident, E1 scattered, and total. And the incident field, is given by a phase factor here, K0, and a time dependent factor, harmonic factor, exponent minus I k omega naught t, and an amplitude and polarization factor here. K is given by 2 pi over lambda, and the omega is given by 2 pi f, the frequency. And now we assume that epsilon 1 is much smaller than epsilon naught, and E1 consequently is much smaller than E0, and this is the first order approximation. Here we have the wave equation again and the first order approximation, and we insert E0 plus E1 for E and E0 plus epsilon 1 for the epsilon, and take only first order terms. we use the rotation of a vector. Any vector is minus the Laplacian plus the gradient of the divergence. And since the divergence is 0, there are no charges, we can write that the rotation times the rotation is minus the Laplacian. For zero order, we can grab all the zero order terms together and get this wave equation here, and that is fulfilled by the incoming field. For first order, we end up with this expression here, in which the E1s are at the left side and the E0s, the well-known fields, incoming field, are at the right side. And as you can see, we have a function of E1 left and a function of E0 and epsilon 1 at the right side. And the problem is now find E1, isolate E1 as a function of epsilon 1 E naught. Here is the problem. And this is the situation: E naught, E1, Ks, K naught. And the solution is given here, and that will be derived in the appendix. And let's investigate the various terms in more detail. Here we have the incident field vector with r prime for the integration over the scattering volume, and t prime, which we will discuss in a minute. Here is epsilon 1, material properties. Here Ks times Ks, the polarization direction, as we will see. Integration over the scattering volume, and here we have the spherical outgoing wave. T prime stands for the retarded time, t minus r prime over c, and that is taken into account the flight time, various flight time from various parts of the scattering volume to the detector. And it accounts for phase differences. And that accounts in the form of an exponential with Ks minus K naught times r minus r prime. And here we have the phase differences. Here is the solution again. And now we will look at this part of the expression. And when epsilon 1 is a scalar function, we can write for the direction of E1 that it will be parallel to this equation here. And let's assume that E0 is vertically polarized, as is seen here. E0 is vertically polarized. Then Ks times E0 will be in this direction, that's perpendicular to Ks and E0. Here. And when we look at this plane in here, then Ks times E0 is pointing out of the plane, and Ks times E0, that is parallel to E1, is pointing in this direction, and it can be seen here, E1. Then we have in-plane scattering, vertically and horizontally polarized, as is seen here, the in-plane scattering. Then Ks times E0 is directed in this way, and E1 will be directed in this way. And here, in the horizontal polarization, Ks times E0 will be directed along the z-axis, and E1 will be directed in the plane. Now you can see that here will be no depolarization, but here E1 has two components along the x and the y axis, and that means that there will be depolarization present. Finally, for the electric field here, we have the intensity That is the autocorrelation function of the field strength, as is seen here, expressed here with the integration over a certain time period in which that time period goes to infinity. And you can see that the intensity is proportional to the field strength squared, and thus it will be proportional to k to the 4th power, or 1 over lambda to the 4th power, which means that short wavelength light will be scattered more than long wavelength light. 1 over r squared, the spherical wave, epsilon squared, and the volume squared. And please note that if that epsilon is a tensor function, not a scalar but a tensor function of the coordinates, then the polarization direction will differ. Let's look at the optical properties. Here we have a plot of the scattering cross-section on a logarithmic scale, and here the particle diameter. And this is just a figure to guide the eye. This function will be derived, and it starts for very small particles with Rayleigh scattering. Then the scatter cross-section will be proportional to the diameter of the particle to the 6th power intensity. Then we have an intermediate region where Rayleigh-Gans scattering is applicable, and for larger particles we have Mie scattering, and for even very large particles we have a scattering cross-section that is twice the geometrical cross-section. We will come to this figure frequently. We start with Rayleigh scattering. Here is the situation. We have the incoming field and scattered field here. This is the scattering volume. And we have two wave vectors, k0 and ks. And now we define a plane of symmetry using k0 and ks. And that plane of symmetry is seen here. And we define coordinate axes, x, y, and z, along that plane of symmetry, as is seen here. Here is ks and k0, and here we have the plane of symmetry. Now we define two planes, perpendicular to k0 and ks respectively, and the electric field, the incident field, will be in that plane, and the scattered field will be in plane 2, perpendicular to the wave vectors. And both fields will have components in the perpendicular and in the parallel directions, as is seen here. Dipole scattering works with a dipole that is induced by the electric field, and that dipole moment, P, can be written as a proportionality constant times the electric field, and that proportionality constant will be seen to be related to the relative dielectric constant of the particle in its medium. We know that E1 is parallel to ks times E0, as is seen here for one polarization region, and the E field has components in two polarization regions, and here is the second one, parallel. And now the expression for dipole scattering is given by the electric field, perpendicular and parallel, is a 4 factor times 1 for the perpendicular and with a sign for the parallel component. And for the intensity we have to take the square, and the derivation will be given in the appendix. Here is the situation again and the formula. And now Lorentz derived for spheres the expression that alpha can be given by epsilon r minus 1 over epsilon r plus 2, and this holds for epsilons in the neighborhood of 1. And that epsilon is related to the refractive index using this relation. Please note that frequently instead of that theta also the angle phi is used, as is seen here, angle phi, in which phi is 90 degrees minus theta, the complement of theta, and that means that we have to replace all the sine theta factors in the formulas by cosine phi's. And then we can write the polar plot of the intensity, and the polar plot of the intensity K0, K0 is the wave factor for the incident field, and Ks the scattered wave factor. Then for the perpendicular case we have a circle, that's at 1, and for the parallel case we have the sine or the cosine function. For one scattering we had this relation, and if we have n scatterers per cubic meters, then we have to multiply with n times v, in which v is the volume, in this case a sphere with a radius a, and then we have this expression here for the intensity. And when there is natural light, is not polarized, randomly polarized, then we take the average of both. And then the intensity will be proportional to alpha squared, and alpha is the dipole response on the E0 field, proportional to a squared, a to the 6th power, the particle radius, v squared, k s to the 4th power, or lambda to the minus 4th power, and 1 over r squared, the detector distance. Here the expression again, and now a general overview. The induced dipole scattering with the scattering wave, another scattering direction with another scattering function, scattering field. In situation 1, there is no depolarization because the E is parallel to E0. But in situation 2 there will be depolarization because the E has two components. The Z component and the component parallel to the XY plane, in the XY plane. When we draw a plot of the intensity as a function of the polar angle, then for the perpendicular case, the non-polarized, non-depolarization case, we have a straight constant function here. Now we go to the second scattering, Rayleigh-Gans, for particles about the diameter. Particles with a radius not very small compared to lambda. Here is the situation, scattering volume, and now scattering from different parts may have different phases, and then we can expect to encounter interference at the detector, and when the distance difference between the two scattering volume elements is unfavorable, then we will have destructive interference, as is seen here. And of course that's dependent upon the angle and the particle shape. And this means that for theta, the following relation holds, that the I function will be decreasing as a function of theta, and it will decrease more when the particles grow larger. And please note that Rayleigh-Gans is an approximate treatment. Rayleigh-Gans phase differences when the particles grow larger, and when we have n scatters per cubic meter, then we had this formula here, and now there is an extra factor, and that extra factor accounts for the phase differences, the delta, and when you integrate over the volume, that extra factor integrates to an r of theta and phi, and that r of theta and phi is seen here. And it can be seen that r of theta and phi is always smaller than 1. The final results, of course, depends on the r function. For instance, let's look at the phase difference between these two wavefronts here, A and B. Then the phase difference will be given by 2 pi over lambda times the distance difference, the trajet difference, and that's seen from A1 over P1 to B1 or A2 over P2 to B2. And the result for natural incident light will be given in this equation here, the same for the dipole as for the dipolar scattering, but now with that extra factor. Here is the phase function again. Some examples. For a solid homogeneous sphere, we have a Bessel function. For an inhomogeneous sphere, you have to integrate over the radius, when the dielectric constant is a function of the radius. And for cylinders, disks, and rods, other shapes, information can be found in Van der Hulst. For tissue particles, frequently example 1, expression 1 or 2 is used, because the particles are mostly can be considered as having random orientations. Now, the plot again, as for I as a function of theta. For dipolar we had this, for Rayleigh-Gans, A, the radius about lambda. We have this decreasing function here with some wobbles, and the wobbles are caused by the destructive interference effects. Now we go to Mie scattering. Large particles, Mie scattering. Again, we will have destructive interference depending upon the angle and the particle shape, and Mie has larger particles, so the interference will be much more severe, and therefore the Mie scattering will decrease much sharply than Rayleigh-Gans. There is a rigorous treatment from the Maxwell equations, and that's done by me and other authors, and for the derivation see Van der Hulst. Now we have, for very small particles, in the non-depolarized case, is constant 1. For Rayleigh-Gans it is decreasing. For me it's even more decreasing. And now we go to other scattering functions like Henry-Greenstein from astronomy. That's an empirical, more or less empirical function with a G factor, and the G factor is, as we have seen, the average of the cosine of the polar scattering angle. Gegenbauer is a function, but we will not deal with that here. Isotropic, constant function, isotropic scattering all over all angles. And peak forward, in which theta naught is related to the width of the Gaussian shape. For Henry-Greenstein, please note here we have a logarithmic scale, and this is the scattering probability as a function of the polar scattering angle, and you will see that for a G factor of 0.9, cosine theta is 0.9, so with very small angles are favorable, and that's expressed here sharply peaked at theta is 0. For G is 0, in fact we have isotropic scattering, and that can be seen as the straight line here. Other scattering models are Groenhuis, Verwiller ten Bos derived a scattering function containing isotropic and peaked forward scattering. Bonner and Nossal have a model with discrete scattering points on a 3D grid, and they use a probabilistic approach of scattering in steps. Patterson, Chance and Wilson used virtual point source for the first scattering event at a certain depth in the medium, and that was also used by artists like Farrell and Patterson and Wilson with an image sources above the tissue surface. Overview of the scattering functions again: scattering intensity, the dipolar, Rayleigh-Gans, me, Henry-Greenstein, the isotropic case. Here we have peak forward depending on the width you choose, and now we go to very, very large particles, as you can see here. Again, the plot of the scattering cross sections. Now we go to this part here, very large particle. There is a factor of 2. Why is that factor of 2? Why is the scattering cross section twice the geometrical cross section? Well, we have scattering from inside of the particle, and you can see that will take away light due to a geometrical cross section G. But it turns out that we also have diffraction around the particle, and for large particles you cannot see that because the angles will be very small. But that will take away, as can be shown, light in a ring with an area equal to the geometrical cross section. That ring is here. And this is the extinction paradox. Why is that? The extinction paradox says diffraction through a hole is the diffraction around an obstruction if the hole and obstruction have identical shadows. That can be seen here. Here's the hole and here is the obstruction. The original field plus the disturbance field behind, that is for the hole, is just the disturbance field only, and for the obstruction it is E0 minus the disturbance field. Now the intensity of the disturbance field, when we leave the static part aside, the intensity of the disturbance field is for the hole E squared, and for the obstruction minus E squared. And you can see that that intensity is the same. Now an intermezzo, some optical properties of tissue and blood. First, the scattering, mu s prime, the reduced scattering coefficient. For dermis at 580 nanometers is about 3 per millimeter, and for blood 1. And for infrared, near infrared, it's smaller. Now we go to absorption. And please note this point here, where the red line and for oxygenated blood and the green line for deoxygenated blood cross. And this means that this point here, these wavelengths here, can be used for oxygen saturation measurements, and that's based on the differences in absorption for lambdas at this side of 800 and lambdas at this side of 800 nanometers. Now some examples of scattering function. First, dipolar scattering, and we have the in-plane and out-of-plane components, the polarized and the parallel and perpendicular components summed. The perpendicular component is constant, the parallel component is cosine squared. It is a linear plot from 0 to 180 degrees. And we use natural light, the average of both polarizations. This is a polar plot in 3 decades. Suppose here is the scattering particle, incident beam is coming in from here, then there is scattering. Here is forward scattering at 0 degrees, and here we have backward scattering at 180 degrees. For Rayleigh-Gans we have destructive interference, and that causes those sharp dips in the scattering probability. And for this is a logarithmic plot here, 5 decades, and this is the polar figure, also a logarithmic plot with 5 decades. Me-scattering has also those sharp peaks, but not that sharp as Rayleigh-Gans, since the particles are larger and the sharp destructive interference will be smeared out a bit. And here is the polar plot. And Henry Greenstein resembles the me-scattering but flattens out all those wobbles. And here is the polar plot. And now we go to the appendices, but that is in movie 2.